Hi, everyone. I want to talk to you a little bit about ionic bonding. This is chapter 7, beginning of chapter 7, section 7.1. We have discussed ionic bonding at the beginning of our class when we learned how to put formulas together and name. And we talked about ionic bonding is an electrostatic attraction between negative cations, negative anions and positive cations, right? And it's that plus is attracted to negative that holds ionic compounds together. That indeed is what an ionic bond is. An ionic bond is this electrostatic attraction. How does that attraction occur? We are going to approach this from something called Lewis theory. Lewis theory says that these atoms will lose or gain electrons in the case of ionic compounds, okay? Ionic compounds form when, for example, metals are willing to lose electrons because they have very low ionization energies. Nonmetals are willing to gain electrons because they have very high electron affinities. It's more energetically stable for metals to lose and nonmetals to gain. One way you can think about why that is Lewis theory says atoms lose or gain electrons to end with 8 valence electrons around themselves. We have seen this when we talked about full and half full orbitals are particularly stable. If you have a full set of s orbitals, okay, thinking about using our periodic table, s orbitals and p orbitals, if you have a full set, how many total electrons do you have in an orbital diagram? There's an s, there's p's, whatever energy level. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Lewis theory says everything wants 8 because 8 is stable. Everything is full of electrons when there's 8 valence total. So this theory about 8 valence electrons is sometimes called the octet rule. Not all elements are going to follow octet rule. Lewis theory doesn't explain what happens, for example, very well in transition metals, but it does explain very well kind of what's going on, why things bond when we talk about main group elements. So again, let's look right now, Lewis theory applied to ions. And we have looked at electron configurations for some main group elements and others. So this question is actually on the in-class examples for chapter 7 that I hand out. And if you are in my class right now, you could go to the folder in Blackboard for chapter 7 and you could see this document, or you can get a copy in class. So let's look at these elements with these electron configurations. What we want to draw for Lewis theory is something called a Lewis symbol. We want to draw a Lewis symbol. The Lewis symbol is going to show the valence electrons as dots. Valence electrons are the electrons that do the chemistry. They are the ones that get transferred around or shared for covalent bonding. So I'm only going to focus on how many valence electrons an element has. Sodium configuration, we know this means there is 1 valence electron on a sodium atom. So a Lewis symbol for sodium would be drawn like that, with 1 dot representing that 1 valence electron. You can think of Lewis symbols as inside a box with 4 sides. Those 4 sides could be representing an s and those 3 p orbitals, okay, we are going to fill in dots around the sides, typically before we start putting 2 dots together. That's by convention. Does it matter which side you start with that 1 dot? Not at all. I could put it there. I could put it there. Doesn't matter, but it's just 1 dot. Let's look at magnesium. Magnesium in group 2A has 2 valence electrons. We see that from the configuration and from our knowledge of its group number. Again, 2 valence electrons, 2 dots, separate sides first. Aluminum, its Lewis symbol would have 3 dots. Again, doesn't really matter where exactly they're drawn. Oxygen, let's think. How many valence electrons does oxygen have? We look at all the electrons in the highest N value shells. 2 plus 4 is 6 valence electrons. Again, this is in group 6A. So I should have been able to tell that without even looking at the configuration. Okay, 6 dots. Notice now I have to have 2 dots on a side, right? It doesn't matter which side has the 2 dots or anything like that. Fluorine. 7 valence electrons in group 7A. 1, 2, 3, 4, 5, 6, 7. Okay. We have talked about this these metals lose their valence electrons to give them an outer shell, a valence shell that is now full of electrons. It's like a noble gas. In fact, that's another way that we say this is atoms want 8 valence electrons around them. Atoms want the configuration of a noble gas, very stable. So we know that sodium will easily transfer away its 1 electron, becoming just a sodium ion. Now the Lewis symbol for these cations, we draw the symbol inside brackets and then put the charge. And this should not have any dots drawn around it, because in this 3rd shell, which was its valence shell, it now has no electrons. That's what we're representing with this image, okay? The fact that in what was its valence shell, there are now no more electrons. And if I look at the configuration of the ion, it is just like a noble gas, meaning it does now have full, half, full. That's a total of 8. Okay, that's what it's trying to go for. So let's look at some of these other ones quickly. Magnesium will give away its 2 electrons. It wants to do that. It's energetically favorable to do that. You see that with its ionization energies, Mg2+. Lewis symbol in the brackets with the charge outside. The cation has no more dots around it. What is its configuration? It is now also just exactly the same as neon. Aluminum, 3+, Lewis symbol, configuration, exactly like neon. Oxygen, nonmetals. This has 6. It wants 8, according to Lewis theory. It wants to be completely full in its orbitals, so it is going to gain 2 electrons. And now what we draw for the Lewis symbol is, again, brackets. We always do brackets around ions in Lewis symbols. Here's my oxygen. And for nonmetals, I am going to show now that it has those 8 electrons. It gained 2. In fact, if I look at my previous picture, there were the 6 it had to begin with. There's the 2 it gained from some source, like pairing up with a metal. Yeah. You do draw the dots. You do include the charge outside the bracket, because this original valence shell is now full of 8 electrons. The original valence shell has no electrons, so no dots are drawn. Fluorine will gain 1 to become the fluoride ion. Symbol in the brackets with the charge, and then draw your dots, representing a full octet of electrons. This set of ions is what is known as an isoelectronic series. So in this isoelectronic series, all of these ions, sodium ion, the magnesium, all of them have the same valence, same electron configuration. What is this down here? Oxygen. It was, using our shortcut, helium and then these two. But when it gained those 2 electrons, what noble gas did it become like? There's my oxygen. It gained 2 electrons. It is now the same configuration as neon, the same as all these other ones. So is the fluoride ion. Isoelectronic. These 5 ions all have identical numbers of electrons in identical orbitals configurations. So something you could be asked is, within an isoelectronic series, order them by size. I think I said let's do smallest, largest to smallest. Radii. Let's go from largest to smallest. This requires some knowledge from chapter 6 about trends of size, but basically, essentially, as you move left to right across a row, the size of the atoms gets smaller. As you move down a column, the size of the atom gets bigger. But once we have ions, which is what we have here, you need to know that almost within a row, anytime you've gained electrons, you've become an anion, the size has gotten bigger. Gaining electrons means the size increases. Losing electrons when you become a cation means the size decreases. And so we got to recall, looking across a row, if I have oxygen and fluorine as ions, as the oxide ion and the fluoride ion, they are significantly bigger than when they were just atoms. Cations, in general, are significantly smaller than when they were atoms, okay? The trend about size decreasing as you move left to right still holds, but you've got to remember that cations are always going to be smaller than anions, relatively speaking. So in our isoelectronic series, we have O2, we have F minus, O2 minus, F minus, Na plus, Mg plus, and Al3 plus. Can you see the size of the ions decreases here between O2 minus and F minus? And then, of course, the cations are smaller and they decrease in size, moving left to right as well. And so, if I order this series from largest to smallest, the largest should be O2 minus, is larger than F minus, is larger than sodium ions, then magnesium ions, then aluminum ions. Another way you could remember this trend about size with isoelectronic series is that the element with the smallest atomic number, you know, we use the letter Z for that. If you go by their Z numbers, the smallest atomic number should be the biggest ion in an isoelectronic series. 8, 9, 11, 12, 13. This should always hold true about size. Smaller atomic number, larger ion size compared to a series. All right. That's all I wanted to talk about with ionic bonding.